My name is Alec, and today I'll be talking about a project I inherited from a former student, Sebastian Dick, and how we go from a differential machine learning network to a density functional. So to start off with, the Cohen-Sham equations were implemented using PyTorch, which is a differentiable package in Python. And so we can solve the equations, we get electron densities and spin polarizations. If we want to learn a GGA functional, we can include density gradients. If you want to go up the ladder to learn a meta GGA, we include kinetic energy densities. And so we have two separate machine learning networks, one for the exchange energy, one for the correlation. And as we train, we reproduce high accuracy or accurate reference data. And since it's implemented with PyTorch, we can automatically get the actual exchange correlation potential. And we can look at the accuracy we do just from training on around 20 different molecules. And so on the bottom left here, we have different functionals evaluated on a given data set. So the greens are GGA functionals, the blues are meta GGAs, and the oranges are hybrids. And so the functional that was trained, ours, XCDIP, was trained to be a meta GGA, and we can see that only training on 20 or so molecules, we do as accurate or better than SCAN, which is a high accuracy meta GGA. And so moving forward, we know we can include various physical constraints in the architecture of the network itself, but we can also try and enforce different constraints by giving it training data that we know should reproduce certain things. So we know that fractional charges and spin systems are linearly related to their fully occupied counterparts. And so that's the current goal, is to implement training that way to see how it improves the accuracy of our network.
Curious, training the exchange and correlation separately, does that help you get a better fit?
Yeah, because so you can implement different constraints on the different networks individually. So we can make sure the correlation energy is not negative versus the exchange different factors. But yeah, it makes it more.
Question on that section from the bottom paragraph in the middle. I seem to understand that the differential implementation enables you to only use the small training set. Is that the right connection, or is that?
Well, it gives us the actual potential itself automatically, as opposed to just getting out some energy. So you can use that potential in different ways, as opposed to just using the network to get an energy.
Okay, so what is it that enables you to use such a small training set? Because normally people are complaining that you need a massive amount of data.
Yeah, so I think it's the way we constrain the network to have physicality in it. So there are different bounds that we satisfy in the network, and I think that's what does it.
Thank you.